for joining us. My name is Nevin Alhaz, and I am a librarian here at Santa Clara City Library. And we are trying to connect our patrons with knowledge, experts, and the new technology, not only providing up-to-date collection, online resources or other services, but also providing variety of programs like this. So we are thankful for our guest lecturers who help us to be the bridge between the knowledge and our diverse community. So we have a special guest from Stanford University, and she is the senior research scientist in astrophysics. Please welcome Dr. Elena Orlando.
On CubeSat projects with these small satellites, and they are very small satellites, like so big, so big or so small. And actually, you can see it here. These are three satellites that were launched from the International Space Station. And it was a pleasure. It's an educational program where the students are involved in designing and in building small spacecraft. And those spacecrafts are very useful because they can be used to test new devices, to be used in space, and also to look for new science topics that can be investigated later on with much larger and more expensive missions. So after that, actually, I tried to make it briefly. So after that, I spent a couple of years doing my PhD in Germany, then in Munich at the Max Planck Institute, and then a couple of years of postdoc, and then I moved here at Stanford, and now I'm a senior scientist at Stanford University since 2010. And now, what I'm doing is a completely different thing. Because during my PhD, I started getting passionate about cosmic rays. So cosmic rays, maybe some of you have heard about cosmic rays, are very small pieces of matter, so very small particles, that are traveling in the universe almost at the speed of light, very close to the speed of light. And they are mostly protons, some electrons, and some heavier nuclei. They come from very, very far away, even much far away than our solar system and far away from our galaxy. And they travel, but I don't want to spoil everything, so I can go on with the science from the beginning. So actually, we see here a very nice picture of the sky, and what catches our attention is that this part here. So we see many points that can be stars, can be external galaxies. And here, this is our Milky Way. And we see stars. It's a very crowded area. And we see also gas. We see that it's dark there. It's dust that There is a lot of dust, a lot of gas. But actually, what are all of these points here? So let's have a look more closely at a small region of the sky. So let's take a very small region, like 1/3 of the size of the moon. But let's go very deeply. And we have this image. This is a wonderful image that is called Hubble Deep Field. And this is taken with the Hubble telescope that is in space for almost 30 years. So it's on space almost for, it's been on space almost for 30 years. And we see here many things, many objects. So we see a star here, and then we see a lot of galaxies. For example, this is a spiral galaxy, like our Milky Way. This, I think it's an elliptical galaxy. And this is also a spiral galaxy. So let's see. Here we are very going deep into space, very deep, very far away. So I remind you that this size here, it's almost 1/3 of the angular size of the moon. So you see the moon on the sky. Let's take 1/3 of the angular size of the moon, and we have this image that contains so many objects. And the very interesting thing here is that we are looking far away, like almost 13 billion years away. So that means that light takes almost 13 billion years to come to us. But this also means that we are looking back in time, because light, the speed of light is constant, it's finite. And actually, when we look far away in space, we are looking back in time. So the light produced by those objects here was emitting 13 billion years ago. So when we look at the sky, when we look at this picture, or when we go outside and during night, a very clear night, we see the sky and that's almost calm, really quiet. There are stars, there is a lot of going on, there is nothing, seems there is nothing going on there. Actually, this is because we look at the sky in the visual band. If we look at the sky in gamma rays, that is very different, because gamma rays identify the most energetic phenomena that happened in our universe. But what are those gamma rays? So some of you may associate gamma rays with the Incredible Hulk of the Marvel cartoon. So this guy is a scientist, and actually, he was exposed to gamma ray radiation, and what happened then after that is that anytime he got stressed, so he turned into an Incredible Hulk. So actually, gamma rays do not work like that. But what are gamma rays? Gamma rays are a form of light. And it is the form of light that we actually cannot see with our eyes. And it's a very energetic form of light. So you maybe heard about the electromagnetic spectrum. And this goes from radio waves, the waves that we can hear, to gamma rays. This is light. This is the same form of light. The only difference from radio to gamma ray is the energy of the light. So we have we go from radio waves and the longer wavelength, and then we go to microwaves, which are the form of light that allows us to heat up our food. And we have infrared radiation that is warming up us. And then we are in the visible band here, light in the sun, ultraviolet here. Part of the sun is emitting in ultraviolet. That's why we have to pay attention and put creams when we stand at the sun. And even at higher energy, we have X-rays. X-rays, we are all familiar with X-rays. So when we go to the doctor, we take X-rays. And then the most energetic form of light are gamma rays here. So gamma rays are almost a billion times, almost a billion times more energetic than the visual light. So actually what they do is identify the most energetic phenomena in our universe, or what we say that is the violent universe. But how do we see gamma rays? So on Earth, we see gamma rays from, for example, nuclear explosions here, like nuclear bombs, and also from radioactive decays, like, for example, cesium-137. While in space, there are many phenomena. I just summarized two of them here. So we have black holes and accretion matter into the black hole. It's emitting and producing gamma rays. And we have also explosions of very big stars that are producing gamma rays. I will talk about that in a moment. So let's see how really gamma rays form. To do that, I have to introduce the concept of cosmic rays that I already introduced a little bit earlier. So cosmic rays, as I said, are the most energetic form of particles. It's not light, they are particles, so very small pieces of matter, like protons. And those cosmic rays are actually coming from the sun, the low energetic cosmic rays. But they are coming even from our galaxy and even beyond our galaxy. So from external galaxies. They are protons, heavier nuclei, and while they come to us, they are bringing the information on how they have been originated and of the medium of the cross before reaching us. So they are very important. And actually, they are almost millions of times more energetic than the particles that we can recreate on the ground, like in accelerators, for example, like LHC. And just to give you an idea, the proton is a very small particle. And the most energetic protons that have ever been detected has an energy of almost a baseball that travels at 60 miles per hour. So that's very energetic. And actually, it is believed that these cosmic rays are created during supernova explosions when the very big stars are dying. They create these cosmic rays. And also the external galaxies, like black holes, they are also creating cosmic rays, supposedly. So here is one of my favorite pictures. This is the Crab Nebula. And actually, this is what is called supernova remnant. So this means that we had a very massive star of almost 30 solar masses, and that at some point died and formed this supernova remnant. So we have some expanding shells, and that we see here with different colors, that goes almost to 1,000 miles per second. So they were very fast. And this explosion actually happened almost 100 years ago. And we know about that because there are some Chinese manuscripts that we found indicating that there was an object very luminous in the sky, even during the day, and that is supposedly the Crab Nebula. So about the cosmic ray origin, as I say, they come from the explosion of big stars. So what it happens is that we have the explosion, this star that explodes. And after that, there is what is called the supernova remnant that we saw. So we have these shells that are expanding, and among these shells, in these shells, we have some particles. And those particles are going back and forward in this front wave, back and forward, until they reach an energy that can allow to escape the supernova remnant. Like, let's suppose it's like when you play tennis. So there is a ball, so you don't have to hit so strong, because then the ball is going back forward, and then at some point it reaches the much higher energy. And so how gamma rays then are formed? What's the relation between cosmic rays and gamma rays? So we have an explosion. This cosmic ray is accelerated and goes out from the shells of the supernova remnants, and it encounters another protons or another element, another piece of matter, okay, like gas or dust or whatever that is there. What it happens is that they interact, so they clash, and so a small particle is produced, which is called pion particle, that decays into gamma rays. And this is actually how gamma rays are formed, from cosmic rays interacting with light or other matter around in the surrounding. And here it's actually the video on, this is a particle that is there in space, and then we are here, we'll see the cosmic rays coming that interacts and produce this particle that is called pion, and this particle have a very short life that decays into gamma rays. So gamma rays are very energetic, as I said. So let's see, even more energetic than X-rays. So they are very dangerous for us. But fortunately, we have the atmosphere that protects us from those gamma rays. And so it's a problem anytime we go into space. So it's a problem for astronauts, for example. And it's also a problem for pilots, because there is less, the atmosphere it's less thick, so it doesn't protect so much anymore there. But here on the ground, we are pretty safe. On the other side, that's then a cone. This means that we cannot detect the gamma rays from the ground. So actually, if you want to see those energetic phenomena that happen in the sky, in the universe, we have to go to space. So we have to build the telescopes and put it on orbit. And this is the case of Fermi, which is a telescope, a gamma ray telescope that we see here. So this is the spacecraft. And the satellite, this telescope, is actually this one here. And here, there are many detectors inside. And it's not like really a telescope as we actually think, like a huge disk or an antenna or like, lenses. It's not like that, because gamma rays has to be different, because gamma rays cannot be bending with lenses. So gamma rays travel through almost anything. So we have to build something else. We cannot use mirror, we cannot use lenses. So we have many detectors here. And just to give you an idea of the size, it's almost as big as myself. So you see here some people here. And it weighs, this structure here, it weighs almost 3 cars. And so the Fermi, also called Fermi Large Area Telescope, because it's very big. compared to previous missions. So it's a big collaboration of countries working on that. So like US, NASA is part of it, Stanford University too, and then there is Europe with Germany, Italy, France, Sweden, and there is Japan, and also some places, some people in South Africa working on that. So the collaboration is almost 400, 500 people. And here you see when Fermi was launched in 2008. And it was very emotional because I was working on Fermi and the scientific cases for my PhD. And you know, there are many people working on that for 10 years. And so anything can go wrong when you launch a spacecraft. So you see, you are waiting for that for years then to do science, and then if something goes wrong, actually you have to rebuild your entire career then from the beginning. But it was going pretty well. So actually in 2008, in June 2008, it was launched, and then the Fermi was, the solar panels were deployed, and the first data came after a couple of weeks, and that was amazing because then we were waiting for the data, so how the sky looks like in gamma rays. So any people then could had the chance just after a couple of weeks of analyzing and studying their source that they wanted to study. And so this spacecraft, so this satellite, Fermi, it's on orbit still since 2008. So last year we celebrated the 10 years anniversary. And it's almost on an orbit of 500 kilometers, orbiting around Earth. And it has a very huge field of view, so it can see the entire sky every 3 hours. So that's pretty amazing. And here you see this, this is Fermi. These are the solar panels. And this actually is the detector. And then we see that, as I said, it's not really a telescope in the sense, in the common sense, but it uses some detectors, and there are layers of detectors, so that one gamma ray, when interact with the detectors, producing other particles, and then we can track back the direction of the gamma ray, and we can see it much better here in this animation. So this is the detector. You see, there are different layers of detectors, so a gamma ray passes through and produces different particles, and then we can trace this particle back and reconstruct the direction of the gamma ray. So actually, this is our sky, the sky, in gamma rays. This is the image taken with that instrument. I explain you a little bit in more details what this means. So this is a projection. So let's suppose what we see, we are here, so we see the universe everywhere. So we are like in a sphere, okay? At some point, we have to project everything, all these images, you know, in 2D in order to study them. So this is a sort of projection. This means that here, we are looking directly to the galactic center. Here. While here, we are looking at the opposite side of the galactic center. And here, we are looking up and down. So the yellow regions are the most bright regions, so where the most gamma rays come from. So from the center of our galaxy and almost the galactic plane. So this is actually our Milky Way in gamma rays. While here, we still have some dim emission, gamma ray emission. And we have some sources here, you see, that are external galaxies. They are not in our galaxy. So this is our galaxy, actually. But so I want to start from this picture here and go into the details of the different sources and the different things that we see in gamma rays. First of all, I like to start with the sun that we see here. And we clearly see the path of the sun also. So the sun is burning. It's a burning source. So it's burning hydrogen and helium. And actually, it seems like a calm and static source when you see it with your eyes. But sometimes it happens something really strange. And what it happens is like what they are called solar flares. This is not an image of Fermi, but it is an image of Sol, which is a telescope looking at the ultraviolet. So this is the ultraviolet sun image, solar image. And so we see here that there is a sort of explosion. So this explosion, also called solar flare, is billions, it's equal to millions of hydrogen bombs. So it's quite a lot. And it happens like in a few seconds. And what it happens is that we see light first. We see also radio waves, so we can also listen to this solar flare. And after 1 to 4 days, we also can see the particles, so the cosmic rays that are generated from here. That's why, because light has a different speed with respect to particles. So it takes longer to get the particles to us. And actually, the particles are the ones that then are producing what we see, the aurora, for example. And also this stuff here are also damaging because they are interfering with radio transmissions, for example. They are interfering with GPS. So sometimes you hear about some solar storms. That's what it happens. So these solar flares. And I want to go back a little bit because I also like to say that this phenomenon, these flares happen cyclically. So the cycle of the sun is almost 11 years. So actually, every 11 years, the sun changes. So it passes from an active to a less active situation. So actually, during an active phase, there are a lot of solar flares. When the sun instead is not active, it doesn't produce many solar flares. And what else is here? So this is the same image as before of Fermi-LAT, but actually integrated in a very small time. So just the time of the solar flares, and we see that when a solar flare happens, actually it is the most brilliant source in the sky. But what is also there in the gamma ray sky? So there are so many sources here, so I underline them with circles here. And it seems that they have a pretty flat distribution, a pretty homogeneous distribution. And when this happens, it tells us something. It tells us that actually we are not looking at the sources in our galaxy, but we are looking far away, so to much more distant objects. And these are what they are called blazars. So blazars are active galactic nuclei. That means that are nuclei, like the ones that we have in our galaxy, but very active. And this is happening because at the center, very center, there is a supermassive black hole. And these supermassive black holes continuously eat the dust and around and the gas around here. And what it happens is this falls down, and some of it is actually released as form of jets. So we have jets of gamma rays here and jets of particles. And when we look directly into the jet there, we see gamma rays. If we look at here, we don't see gamma rays. If we look at inside here, we see gamma rays, and we call it blazar. So there are almost like more than 2,000 blazars, more than 2,000 of these objects detected by Fermi. And those blazars also are not just static sources of gamma rays, they are also flaring. And you see here, that should start. Okay, so here there is the northern hemisphere seen by Fermi, and this is the southern hemisphere seen by Fermi. And you see how the sky varies during time. These are some like, I think it's like 30 hours of integrations, 30 seconds of integration. So actually, you see that the sky is changing. So we see here a source that is flaring, and we see also here a source that is flaring. And the same we see here. So there is no source, and here a flare source comes up. So often, we don't know that here there is a source until we detect a flare from it. So when we detect a flare from it, we can safely say, okay, that is a blazar. But what else there is here in the sky, in the gamma ray sky? So there are different objects, like we see some objects here, we see another one here, very bright, and also here. So this is Vela, this is Geminga, and this is the crab. So there are supernova remnants. And actually, the supernova remnants, as I already said, are the remnants of the very big stars that died at some point at the end of their life. So what it happens is seen here in a visual image, actually. So we see there is a massive star here. At some point of the life, the star is not burning. The fuel in the star is over, and actually what it happens is that the nucleus contracts, and the external shells are exploding. And here we see that this explosion produces brightness that is much more like billions of times brighter than the sun. And this happens almost 2 to 3 times a year in our galaxy. So actually, if we want to look at those objects, we have to wait. Or there is the other option of looking at those objects in the external galaxies, where there are so many. And actually, the interesting thing is that those objects here are producing the very heavy elements, like even to silicon, iron, carbonium. All those elements are produced by those supernova remnants, the supernova explosion. And when a star dies, so when we have a very massive star dying, actually what we can see in gamma rays is what we call the long gamma ray burst. So this is the sky, again in gamma ray, and we see a very bright spot there. This is a gamma ray burst that can last from 2 seconds 2 hours, and it becomes the most powerful object in the sky in gamma rays. And actually, it's pretty funny how they were discovered, because it was in the late 60s, so during the Cold War, and US discovered that there were some gamma ray activity going on, and US was thinking that the Soviet Union was doing some nuclear tests. So actually they put the Vela satellites on space to follow, to monitor this activity, and they find out so many gamma ray bursts coming from very far away from space. And there is almost 1 gamma ray per day. So here, there is a video showing how a star, a very big star, like a massive star, can die. So you see, the star is contracting in the nucleus, and then the shells are expanding, and actually the material, it forms some jets. And these jets, when we look directly into the jet here, if the jet points to us, actually we see a long gamma ray burst. And what it remains is a supernova remnant. But so I say there are long gamma ray bursts. That means that there are also short gamma ray bursts. Yeah? And actually, to speak about short gamma ray bursts, I have to introduce a little bit of gravity and general relativity. And so that was hypothesized by Einstein in 1915. So each mass produces a curvature in the space-time. So actually, the gravity with Einstein is not seen as a force, but it is seen as a curvature of the space-time due to a very heavy mass. And actually, the bigger the mass, the higher the curvature. You see, this is a smaller mass produces a less curvature. So what it happens is that any time a mass is moving, is accelerating, it produces gravitational waves. And this is what happens. Like, for example, we have here 2 masses, and these are the gravitational waves, a representation of the gravitational waves. You see, the masses are orbiting around each other, and they are producing ripple in the space-time net, and they are producing gravitational waves that can be seen like if you throw a stone into a lake. The same thing. And actually, what happened in 2015 is that for the first time we could detect the first gravitational wave ever. That was hypothesized by Einstein. And this actually brought to the Nobel Prize in 2017 in physics, by those guys here. And we have seen a merger of 2 massive black holes, almost black holes of the mass of 30 solar masses that merged into another, producing possibly a larger black hole, and also 3 solar masses went away in energy, producing the gravitational waves. So actually what we detected, it was a stretch of the space-time, of the space. So there are some instruments like Virgo and LIGO that are measuring really small variation in space, like 1,000 per 1,000th of the size of an atom. So that's the accuracy that we can reach and we can measure. And there is not just black holes that can merge and they can produce the gravitational waves, and that they can produce also the gamma ray burst, but there are also neutron stars. So neutron stars, just to give you an idea, this is the size of our sun, this is the size of our Earth in comparison, and actually this is the size of the neutron star. We cannot see, it's not an arrow really, actually it's really small. And what does it mean? And this means that the size of a neutron star is like having two solar masses like compressed into a mass that has almost the size of San Francisco. So that's very small. And that's very dense. So what happened a year later, like in 2016, we detected the second gravitational wave. And this time, we also detected light from it. We also detected a gamma ray burst. We didn't detect it the year before. And what it happened is that it was that two neutron stars, they merged here, and then they produced a gamma ray burst. And we have seen a signal of almost 100 seconds in the Virgo and LIGO instruments, and a signal and the gamma rays of almost 2 seconds, less than 2 seconds in Fermi. And I show you here. I forgot to tell you actually that this event here happened 130 million years ago, because we see this event happening 130 million light years away. That means also back in time, where here we were at the epoch of the dinosaurs. So I show you here what we think is going on. These are simulations, so this is not the real thing that we see. So you see there are two neutron stars that are orbiting, and then at some point they merge and they produce huge jets. And we see the jets here in this direction, and we saw actually the gamma ray burst. But so why is it so important to see gravitational waves and also the light counterpart? So let's suppose that you are outside Niagara in a square, and you never seen any airplane. You just saw a picture of an airplane, okay? So you don't know anything about an airplane. And at some point, you cannot see, but you hear an airplane passing by. So you say, okay, that's some noise, that's something, there is something, it can be an airplane, it can be anything. What is that? This is what actually we have done when we detected the first gravitational wave. So we heard the sound of the wave. We heard the sound of these black holes that were merging. But we didn't see them. So actually, it's just when you can use also your second sense, like you can see the airplane passing by, then you associate the airplane with the sound. That's why it's so important to see also the gamma rays from this event of the gravitational wave. So we can study this event much more clearly. We have a much more clear description of it. But why are those violent events very important, so important to us? So, first of all, it's because those violent events are creating the universe as it is. So, it's the universe that has the possibility of hosting life. And also because actually we are really coming from those really energetic and violent phenomena. For example, as you see here, we are formed or mostly of oxygen, carbon, hydrogen, and nitrogen. All of these elements are coming mostly from exploding massive stars. So if there are no massive stars, actually, I mean, you cannot be here. So the massive stars explosions, so explosion of very massive stars are producing almost all the elements that are necessary to have the universe as it is and to have the possibility of creating life and humans. And so I want to finish with this slide. So a small summary. So we have seen cosmic rays, which are very small pieces of matter, particles, actually mostly protons, that are traveling in space and are coming from very far away. We can detect them here, and they are coming even from beyond our galaxy. We have seen gamma rays, which are very powerful form of light. They are produced by cosmic rays, actually, that are interacting and then are producing gamma rays. Fortunately, the atmosphere protects us, but anytime we want to see the sky in gamma rays, we have to go into space. And that's why I also introduced Fermi, Large Area Telescope, which is a satellite that is taking a very nice picture of the sky in gamma rays since 2008. And this is one of them. This is our galaxy and also the entire sky in gamma rays. So this is the galactic center, which is much more brighter than the rest. And we also seen that there's some different phenomena in our universe that produces gamma rays, so like solar flares, like explosions of stars, very massive stars, and that create supernova remnants. And we have also seen blazars. And also we have seen also the gravitational waves, and we discussed long and short gamma ray bursts. So actually, I like to take advantage of advertising a little bit. So if you are much more interested on knowing much more stories about the universe in the winter term, there will be a class at Stanford Continuing Studies about this and also about cosmology. And I'd like to take a couple of more minutes just to say that why astrophysics is so important. Why doing astrophysics is very important. To me, it's very important because I have a personal preference. So I like to discover things, how they work in our universe. I like to explain how the universe was originated. I like to know how what is happening there. I like to see the laws, the physical laws that can describe all the phenomena that we see. But actually, this is my curiosity. So it's not the curiosity of everyone. So that should be something more important to justify the studies in astrophysics. And actually, it's also because we can learn quite a lot of stuff, and then we can try to apply also the same laws on the ground. But actually, we cannot create such a very powerful phenomena as is going on in the universe. So we have to study them there in order to then learn how it works and actually how these laws, physical laws that we find, can be applied to us. And here there are more concrete examples. Like I just picked a couple of them, but there are thousands maybe. So like this is the space station. So there is actually, we have to, at the space station, we have to measure the density of liquids in the space, like the fuel or anything that we have. And the instruments and the mechanism to measure the density of liquids actually now used, that was used and was in the space from created by NASA. Now it's used to measuring the density of blood. So actually it's very important for us. And for example, there are also some materials that have been created and used for space devices, and like carbon fibers that are very light and then can be used now and are very important, for example, for prostheses. And another example, like a very small example, like special glasses that were used to identify fire in the electronics for during the launch of NASA missions, now are used by firefighters in order to identify the source of the fire. And also with our cell phones, for example. So the CMOS is a sensitive sensor for digital camera now that is used in our cell phones, but actually it was used by NASA in space. But there is a long list, like of course GPS, long distance calls, and all the researches that are done in microgravity are done in space. And actually also astrophysics, the thing that I really like the most is that we are collaborating with many people around the world. So from Africa to Japan to Europe, US, anywhere. And actually, this is an example of a very Pacific collaboration where there are no boundaries. And this is, I think this is the most beautiful thing. So thank you. I leave it with a summary here. And I really thank you for your attention. Is there any questions? So I'd be happy to take it. The blazar is the same object as a quasar. The blazar, the difference is that with blazar, with the definition of blazar, we are looking directly into the jet. So that is the one that produces gamma rays. But that's the same object seen in different. Yeah. That's a good question, actually. You were first. Mm-hmm. Yeah, I mean, the atmosphere, it's protecting us, right? And of course, if there is no more atmosphere, we have much more gamma rays penetrating that, and the gamma rays and also cosmic rays. So, yeah, I mean, we have to keep an eye on our atmosphere. Can you rephrase the question? I didn't get it.
The lower level, the center image.
This one here?
Yeah.
Okay.
As that was moving, it appeared to be activities that would be forming like a hurricane or something. Is that possible?
A hurricane? I don't think this association has been investigated. There is almost one gamma ray burst per day that is detected far from distant galaxies. And The number of gamma ray bursts is almost constant, and that's always been the same. So it's almost one per day. So I don't think there is any association with. So many questions, I don't know. I don't know who was first. So let's go this way then. Almost all gamma rays are absorbed by the atmosphere. Yeah. Yeah.
You have a source of gamma rays in the sky. How do you figure out how far away it is?
Sorry, can you repeat the question and the answer?
Oh yeah, sure. So the first question was how many gamma rays are absorbed by the atmosphere. Actually, almost all gamma rays are absorbed by the atmosphere, fortunately, so this allows us to live here. Sorry, can you repeat the question then?
When you have a source of gamma rays in the sky, how do you figure out how far away it is?
That's a very good question. Actually, when we look at that, we look also at different wavelengths. And like, for example, in infrared, and you see the, so to look at the distance, to know the distances of the objects, we use like very often what is called the Doppler effect, and or the redshift, cosmological redshift. So actually the light that should be at given frequency, it's seen like much more reddish. And from there we can infer how far away is the source coming from. You were first, I guess? Okay, yeah? Yeah. Oh, okay, so the question is that there are two kinds of gamma ray burst, the short and the long one. So the short gamma ray burst, the long gamma ray bursts are the one produced by explosion of very massive stars. The short gamma ray bursts are the ones produced by merging of black holes or even neutron stars. So in both cases, they are producing short gamma ray bursts. Short means less than 2 seconds. Long means more than 2 seconds. It can also be like hours. Yeah.
How are undetectable on Earth? How were they originally detected?
So the question is if gamma rays are not detectable on Earth, how they originally detected. So the case of the gamma ray burst, it was detected by the US because, as I said, it was during the Cold War that they were detecting gamma rays, and they were thinking that Soviet Union was doing some tests, nuclear tests. So actually, they put Vela into space. There are like some satellites with some detectors for gamma rays. They found out gamma rays from that, and they found out that actually it were coming from very far away. Yeah.
Since our atmosphere protects us from gamma rays, is one of the problems then with setting up colonies on the moon or Mars the fact that since those places don't have an atmosphere, there would be nothing to protect the colonies from gamma rays?
Yeah, that's correct. Actually, it's not only gamma rays. Actually, it's also cosmic rays. So cosmic rays are what is called ionizing radiation, which is the one that is very dangerous, like gamma rays. And that means that they can penetrate, they can change, you know, the molecules. And they are very dangerous for us, and they are also dangerous for devices and in space. So for a few, like a mission, like astronauts are very exposed to those radiations. Pilots too, and for a future mission for like colonizing other planets or Mars, or that's a very big project, problem. I think that is the most important issue, actually. Yeah.
You said the solar flares on the sun, they produce like hundreds of like hydrogen bombs?
Yeah,
The capacity of the energy?
millions of hydrogen bombs. It's the
Yeah.
same energy that is released.
Someone told me once, they say the sun compared to other stars, that's like not even a whole lot of energy compared to other stars in other solar systems. Is that right?
Mm-hmm. Yeah, there are much more powerful stars, actually. So there are like stars that are very big, like even 60 solar masses. So 60 times our sun. These are very, very big objects. Yeah. Oh, yes. Many, many. Especially in our galaxy. So it seems like, you know, we live here in our galaxy, is pretty close. We should know everything about our galaxy. But actually, what it happens, especially at the galactic center, is not known. At the galactic center, there are many sources, and there is a lot of confusion. And there is a region where also we expect dark matter, the signal, that can be also seen in gamma rays. And in this case, there are some gamma rays that are not explained now, or at least they can be explained by many options, many possibilities. And we don't know exactly how they can be really explained. And there is also, this is an example, I can give you another example, like there are, in gamma rays, there are very huge structure, like lobes, you know, coming out from the galactic, that seems to coming out from the galactic center, and they extend to very, very high in the sky. And actually, we don't know exactly what it is. That can be like a signal of a past activity of our black hole in our galaxy, because our galaxy is hosting a black hole, a very massive black hole. Fortunately now, our galaxy is not active as the blazars that we have seen there, so it's almost quiet. But in the past, it could have been active. And it can also be possible that these structures that we see are like sort of remnants of this activity in the galactic center. These are just a couple of examples, but there are many. Yeah. Oh, yeah, good question. So the black holes evolved, I would say, like billions of years, because they started like almost the first black holes like a billion of years after the Big Bang, so they have almost 13 billion years, and they evolved. They actually, they also can merge together to form a much more massive black holes. So yeah, there's like a billion of years of evolution in that case. Yeah. I'm sorry. Mm-hmm. No, it's a big issue. The radiation, like from gamma rays and cosmic rays, is the biggest issue for space missions, any sort of space mission. So that's a very big issue, yeah. Yep. Yep, please.
Gamma rays can only be detected if that jet is pointing towards Earth, right?
Mm-hmm.
So does this mean that the photograph that's taken by Fermi there in the top right corner, it's not showing everything, it's only showing a small percent of activity?
Okay. These are like some flashes, bursts. And so this image here, that's a very good point, because I have to tell you something more then. And so this image here have a lot of sources. These are the ones that point to us. But then you see that there is also some other, like some other gamma rays here, like the bluish. And this is a sort of combination of sources that are not resolved by the instrument. This means that actually we don't have, the instrument doesn't have the sensitivity of resolving these sources itself. Like, let's suppose when we see a light, when we see, we are in a street, and we see a car coming to us, and it's night, and they have lights on. So if the car is very far away, we see just one light. While the car is approaching, we see two lights, right? So this is the point. So actually, looks like a sort of a diffuse emission, diffuse gamma rays, and this is because there can be many sources that are not resolved, like the lights of the car. And it's also because there is very diffuse emission. And I'm going a little bit more into the detail now. It's very technical. So those cosmic rays, the cosmic rays actually that travel in our galaxy, are also interacting with the gas and the photons in our galaxy. They are almost everywhere. So anytime they make a very small path, they are interacting, they are producing a gamma ray. And this actually results in having a sort of diffuse, like a fog, diffuse emission like a fog. And so these are the other forms of why we see almost all of these images in this way. Yeah.
How come the lasers, jets, why do they specifically go up and down in that specific direction? Can it go in any other direction?
Actually, no, because this is usually this structure is rotating. So the gas is forms a sort of torus around the source, and the gas, when it doesn't go into the black hole itself, it then goes like in the opposite, in the perpendicular directions. So that's why you just have the torus that is like this, and then the two jets. Okay, sure. It was coming from there, yeah? I have to come closer. Yeah. Mm-hmm. Thank you for the question. So actually, not all the gamma ray sources are. Yeah. So the question was if there are. I said at some point that the sources are distributed almost in the same direction of the sky, and those are the sources that are much far away, so outside our galaxy. So. This is a good point, actually. So if we look, let's see if I can put the... Yeah, this one. Okay. So this is our Milky Way. So if we look at the sources in our galaxy, they come mostly from this region here, because they are closer, and because the galactic plane contains a lot of sources, many more in the plane than up and down. And actually, So if we see some sources that have this distribution, so much more sources here and less sources here, we say actually usually they are of galactic origin. So anytime we see something that it is distributed very uniformly in the sky, that means that it doesn't have any structure, preferred structure, any preferred direction. So that means that they are faraway sources, so outside our galaxy. So they are most likely external galaxies or some external objects. Yeah, sure. I'm sorry. Oh, we would not be here. Yeah, actually. So the question is, what if the sun is 60 times have 60 times higher mass than it has now? So we couldn't live here. With 60 times, well, actually, it would be big as the distance from the sun to Earth. So actually, yeah, so the diameter of our sun, it's 100 times the diameter of the Earth. So actually, the Earth would be almost contained into the sun. And but not just that. It's that a star of 60 masses would behave much more differently from our sun. Would have a different radiation, and so the Earth would not be here as it is now.
Thank you, Dr. Rolando.
Thank you very much for coming.